Hello, my name is Scott Schenker, and on behalf of my many co-authors, I will be talking about the InterEdge. I want to call out for special attention the two student leads on this project, Lloyd Brown and Emily Marks. We are all very familiar with the canonical SIGCOMM design talk. It starts with a technical problem, then presents a technical solution, and ends with a quantitative evaluation with many graphs. These talks are great, and you will hear many of them over the next few days, but I need to warn you that this talk will be completely different. I will start by describing not a specific technical problem, but a more general ecosystem problem. The solution to this ecosystem problem is not a narrow technical solution, but a broader architectural one. And the evaluation is qualitative, not quantitative, because the goal of the architecture is to achieve qualitative goals like extensibility and interconnection. So let's get started by asking, what is the ecosystem problem at the Internet's edge? To explain this, let me go back in history to ask, what was the secret of the Internet's success? Most people would answer the Internet architecture. And that's right, but it is hardly a secret anymore. I think the most underappreciated reason for the Internet's success was its infrastructure, which had three crucial properties, none of which were determined by the architecture. One, the interconnection of ISPs. This allowed a global network to be built out of many smaller networks and allowed coverage to be extended by merely adding a new ISP in a currently unconnected region. The important point here is that the coverage of the Internet is the union of the coverages of the ISPs. Two, network neutrality. Among other things, network neutrality prohibits blocking or extracting more revenue from certain applications. This prevented the carriers from charging hyperscalers for access for their customers. Three, any-to-any connectivity seems natural, but one could have built a hub-and-spoke network with all content providers at the hub. Any-to-any connectivity allowed popular sites to arise anywhere. So these three properties made the early Internet a wonderful platform for enabling innovation. So where has that innovation taken us? What does the current infrastructure look like? Well, the current infrastructure is a hybrid of the old and the new. It still has the classic Internet, where traffic goes from an access ISP to some transit ISPs to another access ISP. But it combines this classic Internet with two other components. First, there are now some private user-facing networks, we will call them UFNs, that connect access ISPs directly to the back-end data centers of some hyperscalers. Second, there are now a variety of edge networking services, things like CDNs and zero trust network access and DDoS protection. Some of these services are built into the private UFNs, and there are now third-party edge service providers, or ESPs, that offer these edge networking services commercially. ESPs include Cloudflare, Fastly, Akamai, and many more. As a result of these changes in the infrastructure, the dominant mode of content delivery is now going directly between access ISPs and the edge, where an edge service can be provided by a UFN or an ESP. This is a huge change in the infrastructure, and it provides much better performance than the classic Internet. This works well, so what's the problem? The problem is about the ecosystem as a whole. Because when you look at the infrastructure, you notice that the new components offering edge services are not interconnected. So the coverage provided by the ESPs is not a union of their individual coverage. It is not neutral because they have no history of such regulation. There's nothing preventing the ESPs from discriminating against specific customers. Not any-to-any, because the UFNs are essentially hub and spoke. None of these factors create technical issues, but taken together, they create several important ecosystem problems, three of which I will mention here. The coverage is now limited to the scope of individual ESPs, forcing content providers to stitch them together themselves if they want broader coverage. Innovation is limited because new edge services typically need to be backwards compatible with what hosts already support, because content providers don't want to rely on the proprietary offerings of a single ESP. And because rolling out new edge services is hard, each one must generate significant revenue. Lastly, and perhaps most crucially, the long-term evolution of the ecosystem is limited by what ESPs are willing to tolerate. Unlike telephony, which had to let the internet arise, and unlike the internet, which had to let the hyperscalers arise, there is nothing stopping the ESPs and UFNs from limiting the next step in what comes next. How do we fix these problems? We claim we need an architecture for the edge, so we can implement these edge services while retaining the desirable properties of the early internet infrastructure: interconnection, neutrality, and any-to-any delivery. So where do we start in designing an architecture for the edge? The starting point for this architecture is obvious. We should use the internet for connectivity because it already exists and provides any-to-any delivery. The core goal of the architecture is to provide the missing properties of interconnection and neutrality. We call this architecture the InterEdge. Just as the internet interconnected ISPs, the InterEdge interconnects ESPs. And for convenience at this point, I'll just use ESP to mean both ESPs and UFNs, so my tongue doesn't get so twisted. In addition, we have many secondary goals. The design should be flexible, performant, and extensible, and it should also make economic sense. So how can we meet these goals? The basic InterEdge architecture is simple. We start by putting general compute clusters at the edge. We call them service nodes, or SNs. This is exactly how ESPs are built, but the difference is that all services run in the same execution environment. Each edge service is implemented by a module running inside this execution environment. The InterEdge thus has a write once, run anywhere deployment property, or WORA. All code, the execution environment, and the modules are open source and standardized by some organization like the IETF. In addition, we require that each service node be equipped with secure enclaves. These service nodes are provided by InterEdge service providers, or IESPs. These providers could be large, like the giant ESPs of today, or small, like community networks, or anywhere in between. And each host must be associated with one or more first-hop service nodes, just like each host needs a first-hop router. Thus, a typical traffic pattern might be to go from a host to its first-hop service node, to its destination's first-hop service node, and then to the destination. There are a bunch of details to this architecture that we cover in the paper. Here, I just want to highlight a few of the technical challenges we needed to address to achieve our goals. First, achieving interconnection is really the problem of how can the service nodes cooperatively implement a particular service. This will depend on the details of the service, but typically this is not very complicated. Flexible yet performant. Flexibility is provided by having general purpose compute, but performance is achieved by having each service carefully identify a fast path, which can be handled in hardware accelerators, and a slow path, which can be handled by general compute, and off-path functions that may require storage or other slower functionality. Extensible. This follows directly from the write once, run anywhere nature of the architecture, enabled by standardizing an execution environment. The economic aspects of the InterEdge are a bit subtle. Please see the paper. It is crucial that it can support services being paid for by hosts or by applications or content providers. and that there is no need for settlements between the IESPs. Everyone is getting paid directly. We require that IESPs publish their standard rates and offer them to everyone. This enforces network neutrality. It also, as we describe in the paper, allows brokers to stitch together coverage for applications and content providers. So I've done a lot of talking so far and still haven't mentioned the kinds of services that the InterEdge can support. I should emphasize that the InterEdge is designed to support edge networking services, not general edge compute. The kinds of edge networking services we have considered should be mostly familiar to you. They include multi-point delivery of various types, privacy measures which are enhanced by the use of secure enclaves, built-in security measures like RPA-KI and DDoS protection, and a variety of other services like message queues and consistency services. And we welcome your suggestions for what would be most useful. We think there is a huge opportunity for the edge to improve application performance, security, and functionality. At this point, you're probably muttering to yourself, what's new here? It is true that ESPs can offer these services today, but what's different is that the InterEdge can provide them universally, at low incremental cost, and in an integrated fashion. So that's a lot of fancy words, but why does this matter? When services are universally deployed, they become part of the internet service model, part of the fabric of what applications and hosts can rely on. That changes the nature of application development and of what we think is feasible. When services become easier to deploy, the pace of innovation increases and can be driven by how useful services are rather than by how much money they generate. Take Redis for an example. This is the kind of cloud innovation that is very useful, but it didn't start with a business model. We hope to encourage the same kind of freewheeling innovation at the edge. If services are offered by a unified architecture like the InterEdge rather than by separate ESPs, then designers can ensure that services can work together. This lack of integration is currently a major problem. The bottom line is that the ecosystem created by the InterEdge is very different and much better than the current edge ecosystem. In any paper, we must show that we have achieved our goals. Here, I can do it in one slide because I've already covered all of these points, and here I've just listed them for completeness. See the paper for more details. But that does leave one more question to address. How could the InterEdge possibly be adopted? I want to be careful about why I am answering this. Adoption is not, and never has been, a requirement for publication. The vast majority of SIGCOMM papers never see adoption or impact deployed system. That's just how research goes. But in most cases, it is easy to understand how a design could be adopted if companies were so inclined. It is much harder to envision how the InterEdge could be adopted because it is not a narrow technical design, but an architecture for an entire ecosystem. So it is an interesting question to think about, and I'd like to provide one answer to it here. Here's one possible path to adoption. It involves building the equivalent of the ARPANET for the InterEdge. This would be a prototype that demonstrates that the InterEdge works and provides value. Then the smaller ESPs might adopt the InterEdge because it combines their coverage and market power and allows them to compete with the ESPs, not just in size, but in lower costs because there is joint software development and new features because there are open source standards that applications can rely on. At this point in my techno fairy tale, some other companies that have large edge presences but don't offer edge services might adopt the existing software solution and deploy it. Carriers fit into this category, as do many edge infrastructure providers. And the happy ending in this fairy tale is that the big bad ESPs decide that they can still retain their market power while lowering their costs and increasing their functionality. And the Edge lived happily ever after. We are trying to make this fairy tale come true by building such a prototype. One has been built, and we are in the process of testing various services. We will soon be open for business on NSF's Fabric testbed. Fabric is mostly within the US, so we hope to increase our international coverage by using nodes being donated by Mibura, a company that has edge locations in 75 countries. This is not just our playground, it is yours too. We invite the research community to join in building new InterEdge services, new applications that use InterEdge services, and help improve our basic infrastructure. We welcome you with open arms and desperate minds. See theinteredge.org for announcements. I want to end with a final and more somber thought. We are very grateful that the PC took a risk on this paper. It is not your typical paper, and it took courage to stand up for it. But I want to encourage SIGCOMM to continue taking such risks. We follow the industry on the cloud, the edge, satellite networking, and more. If we are going to lead industry rather than follow it, we must take risks. We will be wrong more often than right, but you cannot create the future without publishing a few wrong-headed ideas. And remember, once upon a time, the reigning incumbents thought the internet was a misguided idea. Thank you.